I'm Mort Schmidt with Cox-Colvin and Associates. We're an environmental consulting firm in central Ohio of about 20 people. And we do the usual groundwater, soil, et cetera, but we've done a lot of soil gas prospecting for VOC sources and vapor intrusion, especially in recent years because of the development of the vapor pit. And I'm going to talk about a little bit about soil gas sampling techniques and how they affect sample quality, and I'll bring it back around to spatial heterogeneity at the end. So, let's see. One common way of collecting soil gas samples is with direct push, commonly called geoprobe. This is a rig that's putting in temporary sample points using post-run tubing. You run the tubing down there, let it sit for half an hour, collect your sample. Good, cheap way to collect data you can't resample very well. If you do want to resample, then you probably want to do something like this, a soil gas implant where you've got a small screen surrounded by a sand pack, separated by bentonite, etc., as in this figure in the back of the Hawaii guidance. And you can go back and do repeat sampling here. Somewhat higher data quality typically. You can do more or less the same thing in a limited space. This figure on the right is from the California guidance, and they recommend, at least one way they recommend of collecting sub-slab soil gas from a very shallow depth immediately beneath the floor, is the same kind of arrangement with a screen and a sand pack and everything constructed in a limited space of about a foot vertically. You can do that. You can get good data from this or from the earlier ones, but this is a rather costly, time-consuming process of typically coring a hole through the concrete first, etc. None of the equipment is very usable. More common approach for shallow sub-slab soil gas, that is through a floor, typically inside a building, is shown in this figure from the Raymark investigation by EPA's Dom DiGiulio. And this figure shows up in a lot of the guidance. And basically he drilled a hole through a slab and put hardware, brass, stainless steel, swage lock, etc., with compression fittings usually, in the slab, and then collect vapor through the slab and into your sample container, canister, sumacan, what have you. This requires cementing around the probe and between the probe and the concrete, and it does have some limitations. You can see that the cement going around there is a relatively small area. They have a tendency to break loose, including to the author here, and to probably about everybody who's tried this. You have to wait for the cement to get set up and typically come back and sample on the next day. You normally would not be able to reuse this hardware. You can get good data from it, but again, those limitations, for which reason we came up with a vapor pen, and I won't talk about this a huge amount. It's in the back of the Hawaii guidance. You can see pictures and SOPs. But the advantage of this is that the vapor pen is held in with a silicone sleeve, so there's no cement to set up. You don't have to worry about getting a complete seal around it. It's got a threaded section on top that you can screw a lid down onto, and you can pull it up when you're done sampling, and a barbed connection instead of compression fitting. Installation is simple. You drill a 5/8 inch hole, dust it out, hammer it in. We've put in as many as 90 of these things in a day, just 2 guys in a hammer drill, so they definitely go quick. On the left, I've got a stick-up configuration. This is if you don't mind having 3/4 of an inch of hardware sticking up above grade. So you put a traffic cone on it, come back and sample later in the day, pull it out and plug it when you're done. If you're going to leave it there for repeat sampling, that would be more typical of vapor intrusion. The stick-up is more common if you're looking for sources, and once you find your VOCs, you pull them out and leave. If you're going to do repeat sampling, you drill an 1.5 inch hole and then a 5/8 inch hole through that, hammer the whole thing below grade, and you can screw this cover on the top of it, run over it with a forklift, walk over it, whatever you want. So much for different sample devices. There's a lot of discussion in the literature versus concerning purging. You've got to get that clean air out of the sample tubing and the sand if you have a sand pack, etc., and you want to get good dirty soil gas in there. So here I'm purging with a multi-gas meter, the yellow device, and well, you can use a couple of things. You can use a syringe and just pull it out until you get the right amount of soil gas. You can use a peristaltic pump, although you don't want to use that for the actual sampling. I'm using a PID. And the advantage is this PID and multi-gas meter, I can read my oxygen. I can see LEL if I have explosive gases, typical in a hydrocarbon situation, carbon dioxide, depending upon the meter. You can see there I've also got a vacuum gauge. That little dial gauge is telling me if it's tight soil. I'm drawing vapors at 200 milliliters a minute, and if I get an indication of vacuum, then I have tight soil. It might preclude sampling, and that'll be useful information later on if I decide I need to mitigate. There are many discussions too on purge volumes. A lot of the guidance, including Hawaii, uses a default of 3 purge volumes before you have good soil gas in your tubing. But you can also, what I like to do and what the Hawaii guidance allows, is to watch your meters. And you can see that the oxygen here, when I start purging, the oxygen drops. I always see that. PID, if you have VOCs, the PID rises. And at the end of the purge period, depending upon your hardware, with a vapor pin, it's typically about 20 seconds. When things level off, then you're ready to sample. Containers, different sample containers will give you different results, and they have their pros and cons as well. If I'm looking for sources, I'll often use these. These are little 22 mil evacuated vials, a little smaller than a VOA bottle for groundwater. They're cheap. They don't have the lowest reporting level. They use straight GC, so we can get down to about 10 parts per billion. That's great for finding sources, may or may not be low enough for vapor intrusion purposes. But I inject my syringe down into the tubing, directly into that's a vapor pin there, stick up. Pull out the soil gas and inject it into the end of that vial, send it off to the lab. Obviously very compact. A lot of people like Tedlar bags. They're cheap and you can throw them away when you're done, so there's no risk of cross-contamination, but they do have limited holding times, typically 2 days, and they have potential interferences, which is to say they contribute some VOCs and take away others. I've used them to transfer gases sometimes, and I might measure field parameters out of them, but I'm not a fan myself, but they're certainly usable too. Bottle vacs, these are made by the same guys who came up with the Encore sampler for soil sampling. And these are disposed of in between, at the end of sampling, so you don't have to worry about cross-contamination. They're a simple device. You cannot take an 8 or a 24-hour sample with them. It's just a 200 milliliter per minute grab sample, but you can get good data out of these. Reporting levels are fairly close to Sumicans, and they come in various sizes, so bulk is not quite the issue that it would be with a Sumican. Of course, Sumicans, presumably you're familiar with. These are regarded as a gold standard for sampling. Again, they'll give good data, but there are issues with the regulators. I found most labs, the limitation is, we've had 1 or 2 really poor labs, and the limitation was not, I don't think, in the analysis, but in the equipment. These can clog, they can leak, sometimes both. So it's very important that you test them before sampling and always have a spare with you. But you can obviously get good data with these. Active soil gas, and just so that it's clear, active sorbents, just so that it's clear, Harry in the second half is going to talk about passive sorbents, where you put one in place and it basically soaks up vapors. An active sorbent, that's the tube here in the upper right, it's about half the length of a pencil, and you can pull vapors through that using a syringe or other devices. I show a pump on the left. It'll pull a known amount of air through that sample, through that sorbent, and that'll be your sample. So a passive sorbent, you don't know how much air it represents. They're compact. They're good for a lot of compounds, including some heavier things and some of the lighter SVOCs, which a Suma canister wouldn't sample. But it's fairly critical. You have to have some idea what you're sampling, what the concentration is, et cetera. You have to pull at the right rate, or you'll get a lousy sample. So you have to have a fair amount of expertise and knowledge before you go in using one of these. I'll talk now briefly about tubing. Just in general, soft tubing shown on the left will give you more interference. It absorbs more VOCs and gives off others. Stainless steel on the far right is the least reactive tubing, but not practical for a lot of field applications. So most people use nylon or Teflon or PEEK over there toward the right. I personally like nylon. Now there are a lot of studies, including Greg Ouellette has often shown, you often see a figure of his. It's a graph where he sent hydrocarbons through 50 feet of tubing. And when the hydrocarbons got to the end of the 50 feet of the Tygon tubing, for example, there wasn't much left. He lost about 90% of his compounds. Teflon showed up as best, nylon fairly close. Various studies, some show one is better, one is the other, but they all agree that the soft tubing is relatively bad. But it's important to keep in mind the context in which you're using it. We use Tygon on the vapor pins to make connections. We don't use it for long length, certainly not 50 feet, but we'll use maybe a ½ an inch of Tygon or less to connect our NilaFlow to the vapor pin. The barb fitting where you saw the vacuum gauge that was held with Tygon tubing. I've got soil gas only in contact with maybe 5 or 6 millimeters of tubing, not 50 feet. So it's very important when you use a softer tubing, you can do that and you can get valid samples, but don't use any more than you have to. I'll show you a couple of slides here where we did comparisons of the vapor pin to other devices that did not use any soft tubing. You can see the same results. This is an investigation we did with Matt Williams of the Michigan DEQ. We had 4 vapor pins next to 4 Swage-Lock stainless steel hardware sampling devices, subslab devices set in cement. And you can see the Swage-Lock data on the horizontal axis, vapor pin data on the vertical axis. You get the same results. And it doesn't matter if you're looking at low or high concentrations, there's no addition, no contribution, or no subtraction from that little bit of soft tubing. A similar study was done by Susie Nowickas of H&P Mobile Labs. This is the one founded by Hartman, sorry. Yeah, but at any rate, but this is a big lab in the vapor intrusion world. You're probably familiar with it. What Susie did here, she had 10 vapor pins next to 10 of the California scheme, where she had stainless steel screens set in cement slabs with a sand pack, etc. And again, you get the same results. It's obvious that there's no contribution or loss from that little bit of soft tubing. So you can use a little bit of soft tubing, use it properly, don't use any 50 feet. Leak detection is another issue people discuss at great length. This is a scheme proposed by Dom DiGiulio, the guy who had that earlier figure showing a type of subslab device, and he tended to have some leaks with his equipment, so he proposed this where you surround your sampling hardware, and especially the point going through the slab, you surround it with helium. Some people use VOCs like isopropyl, and if you have helium or isopropyl in your sample, he's getting real-time readings with the device there on the left side, then you realize you have to fix it, you tighten up, et cetera, till you have no leaks. You can do that, but you're not going to do very many of them in a day. It's obviously cumbersome, it's costly, it's difficult to carry, you can't carry the helium on an airplane, et cetera. So I like a simple vacuum test. And again, this is approved in the Hawaii guidance. And Susie Nowickas commented here last year that shut-in test is the most effective way to identify and prevent surface leaks. I agree completely. This is obviously not a real sampling device on the left, but just to show the concept that barbed fittings work great if you have the right size fittings. I have more than 20 connections here. I put a vacuum on it with a hand pump, and 5 minutes later, my vacuum gauge shows the same pressure. I didn't have a leak. As to the point going through the slab, you surround it with water. There's a stick-up point on the right. I just surround it with distilled water using a piece of PVC pipe and some Play-Doh. If I have a flush mount, then I can pour the water directly into the 1.5-inch hole. If you don't lose the water, it didn't leak. And if you have good hardware, you won't see any leaks. I've never had one using this device. All right, I'm going to bring it around a little more now to sample spatial heterogeneity in soil gas. This is a case study from a site that we investigated in Western Ohio. And this is, well, it's typical of a lot of sites. We had several suspect sources. We had PCE and TCE decreasing, a couple of defunct degreasers, a couple of above ground storage tanks, and we had groundwater contamination coming from under the building. But we had not investigated in the building, and it was a little unusual because for various reasons, the client told us, I'd like to know if we have any contamination under the building, and I'd like to know it in the next few weeks. And you know how it is, you can collect soil samples, send them to the lab, get back your results. Reiterative processes can take months or years. But we had just developed a vapor pen, and we said, well, we think we can do this in a few weeks, and our approach was to collect subslab soil gas points in a 20-foot spacing, collect samples from them, send them to the lab. And this is what we saw. Using the field instrument, just 2 guys and a hammer drill, we'd put in about 30 points a night, screen them, sample them, pull the points and plug them, and then do another 30 the next night. We did 144 in a week. And we found high levels of soil gas where you've got the big black circles on a logarithmic scale. So those are pretty high levels. And they don't look anything like where we thought the contamination ought to be. That's kind of curious. We followed up with those small glass vials I showed early on and sent them to the lab. What we do now is we would normally send only the hot ones on the basis of the field PID. We'd send only a select number of samples to the lab instead of having to analyze all of them. But at that time, we were paying $100 a piece for the little glass vials. And we get the same kind of data, except we can see which compound is what. Blue is one compound, red is another. We followed up with soil sampling, but it has the advantage we sampled only now over a relatively small part of the plant instead of having to carry a geoprobe and core big holes through the floor everywhere in the building. And the soil contamination looked pretty much exactly like the soil gas contamination. I'll mention too here that the soil is contaminated at a depth of about 15 feet. Your contamination doesn't have to be right under the floor. So how did it get that way? Why is the contamination not where we thought it would be, where the magenta rectangles are? When we look at site history using Sanborn maps and aerial photos, you can see the buildings in 1924. In 1933, the previous owner had purchased a house, started building stuff in his garage, maybe using solvents, we don't know just when. By 1938, his building, though, had expanded to look like this gray T-shaped thing. Another couple of expansions, but by 1950, the building looked like this. Now you notice that your contamination, this is of course the grease and soil contamination, looks a lot like the location of loading docks and back doors. By 1950, the building had expanded to look like this. That blue contamination, the PCE contamination, especially on the left, must have happened before 1952. Now think about this, when you do a facility investigation, you always look for the old guy to ask him questions. There's nobody around who's going to remember what happened in 1952. So you just have to collect a lot of samples to get this kind of information. The building had expanded to its current configuration in '66 and looks like this. So the implications now for vapor intrusion. This is a graph I pulled out of EPA's vapor intrusion database from 2012, where they compared attenuation factors for soil gas, subslab and exterior, and groundwater. And this is a graph showing the empirical databases similar to the one that some of the stuff that Roger showed early on. They collected indoor air, they collected subsurface data, and they compared them. What is that empirical attenuation factor? If you look at the subslab on the right, I've heard people say, well, subslab is no good because subslab is a poor predictor of indoor air. It's true, it's a blunt instrument. There's quite a bit of slop. If you look at their plot, if you look in between the 5th and the 95th percentile of attenuation factors, there's a factor of 81 variation. So if you use your subslab data out of EPA's database to predict indoor air, you can get a different answer by a factor of 81, depending upon where we were looking. Groundwater, though, is more variable. The variability in the attenuation factors between the 5th and 95th percentile is a factor of 330. Exterior soil gas is a variability of a factor of 3,300. It's 40 times sloppier than subslab soil gas. So subslab may be a blunt instrument, but it's the best thing we've got before going into indoor air. Just to compare temporal and spatial variability, I don't have time to go into these radar plots. I've given a couple presentations and I can send you information if you'd like on this. But this is a device, a method I came up with to compare subslab and various kinds of soil gas very quickly. And just focus for now on the polygon shape. The concentrations are lowest in the middle, they're highest on the outside on a logarithmic scale. You can see the indoor air, which are the blue polygons on the left, are fairly variable. Now I'm showing in this slide temporal variability. So I'm showing indoor air on the left, subslab soil gas on the right. And you can see that my variability, one location on different dates, my variability is much greater in indoor air. I have about an order of magnitude difference there. Whereas my subslab soil gas, my variability is very low. My PC, TC, DC varied over a year by no more than a factor of 3. And that's consistent with what Tom McHugh and various others have seen in soil gas. Spatial variability is another story. From the same facility on the left, you can see now my polygons for indoor air. These are taken at multiple locations, but on a single date. So that spatial variability in indoor air within this building, at least, is very slight. Those polygons on the left are all the same shape. The polygons on the right for subslab soil gas are extremely variable. You get a lot of variation over just 20 feet or less. So your biggest problem: tubing type, purge volume and rate, sample type and container, or your leak detection method. I hope you said none of the above. It's spatial heterogeneity. Going back to my earlier case study, if you look at the heterogeneity now in this building, even just looking between the first and the third quartile, just my central, half of those 144 points, my PCE concentrations vary by more than 2 orders of magnitude. And so you have to either collect a lot of samples to get around a building like this, or any kind of soil gas is variable enough. You have to collect a lot of data, or you have to collect larger data. You have to collect samples representing larger areas. So with that, are there any questions?